Hi everyone, it's Mr. Grant here, and today we are going to look at our last topic related to Arene reactions, which is the inductive effect. Earlier, we learned that Arene compounds engage in electrophilic substitution reactions because of their delocalized ring of electrons, which is very attractive to electrophiles. Well, some Arene compounds are more reactive than others. It all depends on what's bonded to that Arene ring. Our basic arene is benzene, which contains only hydrogen atoms bonded to the ring. So what happens when we substitute in different functional groups of those hydrogen? Well, some groups have an activating effect on the ring, making it more reactive, while others have a deactivating effect on the ring, making it much less reactive. Substituents that contribute to the electron density of the ring would make it more susceptible to attack from electrophiles. Groups that contribute electrons tend to be partially negative and or contain lone pairs on the atom that's directly bonded to the ring. Alkyl groups, for example, are weakly activating because although carbon does not have any lone pairs, it is slightly negative due to it having a higher electronegativity than its bonded hydrogen. We can see this in the fact that a compound like methylbenzene or toluene reacts 25 times faster than just plain benzene. Amine and hydroxyl groups similarly are powerful activators because the N and O atoms that are bonded to the rings in these substituent groups have a significant partial negative charge, as well as having lone pairs, one lone pair on the nitrogen and two on the hydroxyl group. This means they'll have a very high electron density around them, some of which will contribute to the delocalized system in the ring. Esters and amides are similarly moderately strong activators. They also have a partial negative charge on the atom that's bonded directly to the carbon ring, but they have this carbonyl group attached to it as well that's going to pull away some of their electron density, reducing their effect. There's also an effect due to resonance stabilization, which you'll see in your textbook, but I'm going to skip over this in this video. You might see it in an advanced course, though. When we number carbons in an arene compound, we give names to the carbon based on their position relative to our bonded functional group. So carbons 2 and 6, the adjacent positions, are called ortho carbons. The next spots, 3 and 5, are called meta, and the carbon opposite of our functional group in position 4 is called a para. So activating groups, they do not make all carbon in the ring equally more reactive. They have a larger effect on the carbon in the ortho and para positions, making these carbon more likely to react. So when we say that activating groups are ortho-para directors, we mean to say that they cause incoming functional groups to substitute onto these carbons rather than the metacarbons with a much higher percentage. A lot of times you'll get 90% or more of the products as ortho or para products, as you can see in this example with toluene reacting with bromine. Okay, in contrast to activating groups, some substituents withdraw electrons from the ring. These are usually groups that have a partially positive atom bonded to the ring. Here are some examples. In each example, we see that the least electronegative atom in the functional group is bonded to the ring. So consider the first example, the carboxylic acid group. This carbon has a substantial positive charge due to it being bonded to two oxygens. The carbon, when bonded to the arene ring, is going to pull out some of those electrons in order to reduce its partial positive charge. This is going to cause the ring to be less attractive to electrophilic attack, and all of those groups that I have listed there have similar effects. This effect, though, is most significant on the ortho and para carbon, which make them substantially less reactive. Okay. As a result, we say deactivating groups are meta directors because they make the meta position most likely to substitute in for incoming functional groups. Do want to note that the metacarbons are still not being made more reactive. They're still much less reactive than they would be with benzene, but the deactivating effect is less on the metacarbons than it is on the ortho and para carbons. One unusual group is the halides. Halides are weakly deactivating. Okay. One of the reasons for this is they have a high electronegativity, which causes them to pull electrons towards themselves and out of the ring. However, they also have 3 lone pairs adjacent to the ring, and these effects sort of offset each other. Although they might make the ring a little bit less reactive, they still direct incoming groups to the ortho and para positions like an activating group would. So keep that in mind. So let's see if you can tell whether these would be activating or deactivating. Our first group is a nitrile group. If you see, the bonded atom is a carbon, and in this case, that carbon is going to be partially positive because it's bonded to a more electronegative nitrogen. So this is going to be a deactivating group. Remember, anytime we have something positive bonded to the ring, it's going to pull electrons away from it. Next, we have an oxide. Okay, oxides are going to be a very strong activating group because it has 3 lone pairs and a negative charge. So this oxygen is all full of electrons and will easily contribute electrons to the bonded ring. Next, we have got an amine. This one, similar to what we learned about amines earlier, is going to be an activating group because that nitrogen is more electronegative than the bonded carbons. It's going to be pulling electrons from those carbons, some of which will be contributed to the bonded ring. And lastly, we have got this positive amine group. Unlike the previous one, this one's going to be a very strong deactivating group. Anytime we have a positive charge, it's going to pull electrons away from the ring. This one, by adding on that additional carbon onto that nitrogen, the nitrogen is no longer has a lone pair, and it is electron deficit. So it's going to be, or deficient. So it's going to be pulling electrons away from the bonded ring to try to reduce that deficit. Okay. If you have any questions, please let me know on Google Classroom or via email. Have a good one.